Imagine looking up at the night sky and realizing almost every star you see might have its own worlds, some like Earth, some completely alien. These are exoplanets, and they've changed how we see the universe. Exoplanets, or extrasolar planets, are planets that orbit stars outside of our solar system. For most of history, we had no proof they even existed. Astronomers wondered, are we alone? Is our solar system unique? In 1992, the first confirmed exoplanets were discovered orbiting a pulsar, a dead, spinning star. They weren't peaceful, Earth-like worlds, but harsh and deadly places. Still, this discovery changed everything. Today, thanks to missions like Kepler and TESS, we've discovered over 5,000 exoplanets, with thousands more waiting to be confirmed, and the number is growing every single year. These worlds come in all shapes and sizes. There are hot Jupiters, massive gas giants orbiting dangerously close to their stars. There are super-Earths, rocky planets bigger than Earth but smaller than Neptune. There are Mini-Neptunes, water worlds, and maybe even Earth twins. The idea of exoplanets isn't just science anymore. It's become part of our imagination. Movies, books, and games all picture alien worlds where new forms of life, maybe even civilizations, could exist. And here's the mind-blowing part. Astronomers now believe that almost every star in the night sky has at least one planet. That means there could be hundreds of billions of exoplanets in our galaxy alone. So, if there are so many planets out there, how do we actually find them?
Finding exoplanets isn't easy. They're far away, small, and hidden in the bright glare of their stars. Imagine trying to spot a firefly buzzing right next to a lighthouse from thousands of kilometers away. That's the challenge astronomers face. So how do they do it? The most successful method is called the transit method. When a planet passes in front of its star, it blocks a tiny fraction of the light. To us, the star looks like it dims just a little. By carefully measuring these dips, astronomers can tell if a planet is there, how big it is, and even how fast it orbits. Another method is radial velocity, sometimes called the wobble method. A planet's gravity tugs on its star, making the star wobble back and forth slightly. By looking at changes in the star's light, we can detect this motion and know a planet is pulling on it. There's also direct imaging, which means taking actual pictures of exoplanets. This is extremely hard, but with powerful telescopes and special filters, scientists have managed to capture images of a few alien worlds. And finally, there's gravitational microlensing. When a planet passes in front of a distant star, its gravity bends the light, briefly magnifying it. This method lets us find planets we'd never see otherwise. Each technique has its strengths. Together, they've revealed a universe full of planets, gas giants, rocky worlds, water planets, and more. But among all these strange discoveries, one question keeps returning. Which ones could actually be habitable?
The planets we've discovered so far are nothing like the ones in our solar system. Some of them defy imagination. There are hot Jupiters, giant gas planets that orbit so close to their stars that a single year lasts only a few days. Their surfaces blaze with heat, sometimes over 1,000 degrees, hot enough to melt metal. Then there are super-Earths. These are rocky planets, larger than our Earth, but smaller than Neptune. They may have thick atmospheres, deep oceans, or landscapes completely alien to us. Some could even be better suited for life than Earth itself. Astronomers have also found water worlds, planets likely covered entirely in oceans with no land at all. Imagine a planet that is one endless sea with waves that never stop. And then there are rogue planets, worlds drifting through the galaxy without a star. They wander alone in the dark, warmed only by the faint heat left in their cores. Every new discovery shows us that our solar system is just one possibility among countless others. The universe is filled with strange worlds, each with its own story. But not all of them are equally interesting. Some might be truly special because they orbit in the right place, where life as we know it could exist.
Not every planet has the right conditions for life. For scientists, one of the most important ideas is the habitable zone, sometimes called the Goldilocks zone. This is the region around a star where temperatures are just right for liquid water to exist on a planet's surface. Too close to the star and water boils away. Too far and it freezes solid. But in that narrow band, water can flow as oceans, lakes, and rivers. Water is key because every form of life we know depends on it. That's why astronomers pay special attention to planets in this zone. They may not all be Earth-like, but they have one of the basic ingredients for life. The habitable zone isn't the same for every star. Around small, cool red dwarfs, the zone is very close in, with planets orbiting quickly. Around hot, massive stars, the zone is farther out, but those stars don't live long enough for life to evolve. So far, scientists have found dozens of planets that sit in the habitable zones of their stars. Some are rocky, some may have water, and a few might resemble Earth in size and temperature. The search for these worlds is more than science. It's the search for a place where life could thrive, and maybe even a place where one day we might go ourselves.
One of the most talked about is Kepler 186f. It's almost the same size as Earth and sits in the habitable zone of its star. It was one of the first Earth-sized planets ever discovered in that sweet spot. Another is Proxima Centauri b, the closest exoplanet to us. It orbits the nearest star beyond the Sun, just over 4 light-years away. Its location makes it a prime target for future exploration. There's also HD 189733b, a gas giant where winds blow at thousands of kilometers per hour. Its atmosphere contains particles of glass, which means sideways rain of molten glass could fall across the planet's skies. Then there's 55 Cancri e, a rocky planet so hot that its surface might be covered in lava. Some scientists even think its interior could be rich in carbon, making it a giant diamond world. And we can't forget the TRAPPIST-1 system, with 7 Earth-sized planets packed tightly around a cool red star. At least 3 of them are in the habitable zone, making it one of the most exciting places in the search for life. These planets are distant, extreme, and sometimes hostile, but they remind us that the universe is full of surprises.
An atmosphere can tell us more about a planet than almost anything else. It controls temperature, weather, and whether life could survive there. Astronomers study exoplanet atmospheres by looking at starlight. When a planet passes in front of its star, some of the light filters through its atmosphere. By analyzing the colors of this light, scientists can detect gases like hydrogen, water vapor, methane, or even oxygen. Some atmospheres are thick and crushing, like Venus, trapping heat and making the surface unimaginably hot. Others are thin or even non-existent, leaving the planet exposed to space. The most exciting atmospheres are the ones that show hints of water or other chemicals linked to life. Even a faint signal of oxygen or methane together could raise huge questions. Studying atmospheres is incredibly difficult, but new telescopes are changing the game. With them, we may soon be able to find worlds with skies not so different from our own.
An atmosphere can completely change the nature of a planet. It shapes the climate, shields the surface from harmful radiation, and in some cases, makes life possible. Without our own atmosphere, Earth would be a frozen, lifeless rock. So how do scientists study atmospheres on planets so far away? The key is light. When a planet passes in front of its star, some of the starlight filters through the thin layer of gas around it. Different gases absorb different colors of light, leaving tiny fingerprints. By studying those fingerprints, astronomers can figure out what the atmosphere is made of. Hydrogen and helium are common, especially on giant planets. But the real excitement comes when we detect water vapor, carbon dioxide, methane, or oxygen, gases connected to the possibility of life. Some exoplanet atmospheres are extreme. On hot Jupiters, temperatures can soar above 2,000 degrees Celsius. Their skies might rain iron or glass particles carried on winds blowing thousands of kilometers per hour. On rocky worlds close to their stars, atmospheres can be stripped away entirely, leaving them bare and lifeless. Other planets may have thick, crushing atmospheres like Venus, turning them into runaway greenhouses. Imagine standing on the surface where the pressure feels like being under the ocean, and the air is hot enough to melt lead. And yet, the search continues for atmospheres that might resemble our own. A balance of oxygen, nitrogen, and water vapor would be a huge discovery, a possible sign of habitability. Even stranger, a mix of oxygen and methane in the same atmosphere could be a strong indicator of life, since those gases don't last together for long without something constantly replenishing them. Right now, our telescopes are just beginning to reveal these details. But in the coming years, with powerful new instruments, we may be able to study alien skies in depth, seeing sunsets on other worlds, storms that rage for centuries, or perhaps even the chemical signatures of life itself.
One of the most fascinating discoveries in the search for exoplanets is the TRAPPIST-1 system. It's a small, cool star about 40 light-years away, much smaller and dimmer than our Sun. But what makes it extraordinary is that 7 Earth-sized planets orbit around it. These worlds are packed in tightly, closer to their star than Mercury is to the Sun. If you stood on the surface of one, the neighboring planets would look huge in the sky, like moons glowing with reflected light. What makes TRAPPIST-1 so exciting is that at least 3 of its planets lie in the habitable zone, where liquid water could exist. All 7 are rocky, which makes them even more intriguing. They could have oceans, atmospheres, and maybe even the right conditions for life. But there are challenges. Because the star is a red dwarf, it often gives off powerful solar flares. These bursts of radiation might strip away atmospheres or make the planets less friendly to life. On the other hand, if they do have protective magnetic fields or thick atmospheres, life could still find a way. Astronomers are studying the TRAPPIST-1 system closely. With telescopes like the James Webb Space Telescope, we're already beginning to analyze the atmospheres of these planets, searching for water vapor or chemical signs of biology. The discovery of TRAPPIST-1 changed how we think about the galaxy. It showed us that entire families of Earth-sized worlds can exist around small stars, and that some of the best places to look for life might not be far away at all.
If we dream about visiting another world someday, Proxima Centauri b is one of the most tempting targets. It orbits Proxima Centauri, the closest star to our Sun, just over 4 light-years away. In cosmic terms, that's right next door. Proxima b is about the same size as Earth and sits in the star's habitable zone. That means, in theory, it could have liquid water on its surface. Because of its location, it has become one of the most studied exoplanets in the world. But being close to a red dwarf star comes with problems. Proxima Centauri is small and faint, so its habitable zone is very close in. The planet probably always shows the same face to its star, one side in constant daylight, the other in endless night. This creates extreme conditions that could make survival difficult. Worse, Proxima Centauri often erupts with powerful solar flares. These blasts of radiation might strip away an atmosphere or scorch the surface, making life less likely. If Proxima b does have life, it would need strong protection, like an atmosphere rich in shielding gases or a magnetic field stronger than Earth's. Still, the idea of a potentially habitable planet so close to us is irresistible. Scientists dream of sending probes to it one day. Projects like Breakthrough Starshot imagine tiny spacecraft pushed by lasers racing through space at a fraction of light speed, reaching Proxima b in just a few decades. Whether it's a barren rock or a hidden oasis, Proxima Centauri b reminds us that the nearest stars may already host fascinating worlds waiting to be discovered.
When astronomers first started finding exoplanets, they expected to see solar systems like ours. But the discoveries quickly shocked them. One of the strangest types of planets they found were the hot Jupiters. These are gas giants like Jupiter, but they orbit incredibly close to their stars, sometimes closer than Mercury is to the Sun. Because of this, their years can last just a few days, and their atmospheres are blasted with intense heat. Temperatures can soar above 1,000 or even 2,000 degrees Celsius. The heat makes their atmospheres swell up and glow. Some hot Jupiters are so puffy that they're larger than Jupiter but far less dense. On others, winds howl at thousands of kilometers per hour, whipping clouds of exotic materials around the planet. In some cases, those clouds may even rain molten iron or glass. What makes them even more fascinating is that we don't know exactly how they form. Did they start out far from their stars like Jupiter and then migrate inward? Or did they form in place under extreme conditions we don't yet understand? Hot Jupiters were the first type of exoplanet we found because their size and closeness to their stars make them easier to detect. They're not likely to host life as we know it, but they forced scientists to rethink what a normal planetary system looks like. They showed us that the universe isn't limited to what we see in our own backyard. Planetary systems can be wildly different and often stranger than anything we imagined.
One of the most common types of planets discovered so far is the super-Earth. These are rocky worlds larger than Earth but smaller than Neptune, usually weighing between 2 and 10 times more than our planet. What makes them fascinating is that we don't have anything like them in our own solar system. Earth is the largest rocky planet here, and then comes Neptune, a gas giant. Super-Earths sit right in between, filling a gap we never knew existed until we looked at other stars. Some super-Earths may have thick atmospheres, trapping heat and pressure. Others could be covered by deep oceans stretching across the entire planet. A few may even be rocky worlds not so different from Earth, just on a larger scale. Because they're bigger, many super-Earths might be more geologically active, with stronger volcanoes and more powerful tectonic activity. This could recycle nutrients and gases, potentially making them excellent candidates for life. At the same time, their gravity would be stronger than Earth's. Walking on the surface might feel like carrying a heavy weight everywhere you go, but that same gravity could help hold on to a stable atmosphere, something essential for habitability. Super-Earths are everywhere in the galaxy. They may be the most common type of planet, which raises an exciting question. If they're so abundant, could some of them be even better for life than Earth itself?
Not all planets orbit stars. Some drift alone through the galaxy, cut loose from their systems. These are called rogue planets. A rogue planet might have been born around a star, but later flung out by gravity, tossed into the darkness of space. Others may have formed in isolation, never tied to a star at all. Out in the void, rogue planets receive no sunlight. They wander endlessly, wrapped in cold and darkness. At first glance, that sounds like a place where life could never exist, but some scientists think differently. If a rogue planet is large enough, it might still hold on to a thick atmosphere. That atmosphere could trap heat from the planet's interior, keeping it warm for billions of years. Some might even have subsurface oceans, hidden beneath layers of ice, heated from below by the planet's core. These hidden oceans could be similar to what we see on moons like Europa or Enceladus in our own solar system. In such sheltered environments, life could still find a way. Rogue planets also spark the imagination for another reason. They may vastly outnumber the stars. Some estimates suggest there could be more of these dark wanderers than there are suns in the galaxy. They are lonely travelers invisible to the naked eye, but they remind us that the universe is full of worlds, many of them nothing like the familiar orbits we know.
When astronomers confirmed the first exoplanet in the 1990s, it was a revolution. For the first time, we knew that planets around other stars were real. Today, just a few decades later, we've discovered thousands. Thanks to missions like NASA's Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, TESS, the number keeps growing. Kepler alone found over 2,600 confirmed planets and thousands more candidates. TESS is adding even more, scanning nearly the whole sky for tiny dips in starlight that signal a planet passing by. Right now, astronomers have confirmed over 5,000 exoplanets. But that's only a fraction of what's really out there. Our galaxy, the Milky Way, has hundreds of billions of stars. If most of those stars have planets, and the evidence suggests they do, then there could be trillions of exoplanets in just our galaxy alone. What's more, Earth-like planets may be common. Studies hint that a significant fraction of Sun-like stars could host rocky planets in their habitable zones. That means there could be billions of worlds with the right conditions for liquid water. The numbers are staggering, but they change the way we look at the universe. Planets aren't rare, they're everywhere. Almost every star you see in the night sky probably has its own family of worlds. And hidden among them, there may be countless places where life has taken root.
Weather on Earth can be intense. Hurricanes, blizzards, and heat waves, but compared to some exoplanets, our storms are mild. Out there, the weather can be truly alien. Take HD 189733b, a gas giant where the skies are made of silicate particles. Winds there whip at thousands of kilometers per hour, carrying molten glass that rains sideways across the planet. Imagine shards of glass slicing through the atmosphere at supersonic speeds. On WASP 76b, temperatures are so high that metals like iron turn to vapor. In the cooler parts of the planet, that vapor condenses and falls as iron rain. It's a world where the weather literally showers molten metal from the sky. Some exoplanets are tidally locked, always showing the same face to their star. On these worlds, one side is scorched in eternal daylight, while the other is frozen in endless night. The thin strip between day and night could host storms that rage constantly, as heat and cold battle for balance. And then there are gas giants with winds that circle the entire planet in a single continuous storm, lasting for centuries without stopping. Studying this extreme weather helps scientists understand how atmospheres work under conditions far beyond anything Earth has experienced. It also shows us how diverse and dangerous alien worlds can be.
When we think of planets, we often forget about their moons. In our solar system, moons like Europa, Enceladus, and Titan
are some of the most promising places to search for life. So what about moons orbiting exoplanets? Exomoons. So far, astronomers haven't confirmed many exomoons. They're much harder to detect than planets, since their signals are faint and easily hidden in the noise. But scientists are searching carefully because exomoons could be just as interesting as the planets themselves. Imagine a giant gas planet in the habitable zone of its star. On its surface, life couldn't exist, but its moons might have oceans, atmospheres, and all the right ingredients for biology. A large moon around such a planet could be a perfect home for life. Even moons outside the habitable zone could hold surprises. If they have thick ice shells with liquid water beneath, warmed by tidal heating, they could support microbial ecosystems. This is exactly what makes moons like Europa and Enceladus so fascinating here at home. The first strong candidate for an exomoon was found orbiting a planet called Kepler 1625b. If confirmed, it would be a giant moon, almost the size of Neptune. Discoveries like this suggest that moons in other systems may be far stranger than anything we've seen before. Exomoons open up a whole new frontier in the search for life. Planets may not be the only places worth exploring. Their moons could be hiding alien oceans and skies of their own. Discovering planets around distant stars isn't just about clever methods. It also depends on powerful tools. Telescopes on Earth and in space have transformed our ability to detect and study these hidden worlds. One of the most important was the Kepler Space Telescope. Launched in 2009, Kepler stared at a single patch of sky for years, watching over 150,000 stars. By measuring tiny dips in brightness, it revealed thousands of planets and showed us that exoplanets are common. Today, Kepler's successor, TESS, the Transiting Exoplanet Survey Satellite, is scanning nearly the whole sky. Instead of focusing on one area, TESS looks at millions of stars, searching for nearby planets that future telescopes can study in detail. On the ground, observatories use instruments sensitive enough to detect the slight wobble of a star caused by orbiting planets. Some, like the HARPS spectrograph in Chile, can measure changes smaller than a walking pace. And then there's the James Webb Space Telescope. With its powerful infrared vision, Webb can not only detect planets, but also analyze their atmospheres, looking for gases like water vapor, carbon dioxide, or even signs of life. Future projects promise even more. The European Extremely Large Telescope, now being built in Chile, will be the largest optical telescope ever made. It could directly image Earth-like planets around nearby stars. These tools are our eyes into the galaxy, turning faint signals into discoveries that change how we see the universe. Without them, exoplanets would remain invisible mysteries.
Most exoplanets are found indirectly by watching how they affect their stars. But in a few rare cases, astronomers have managed to take actual pictures of them. This is called direct imaging. It's incredibly difficult. Stars are so bright that their glare drowns out the faint light of nearby planets. Imagine trying to spot a tiny firefly right next to a floodlight from thousands of kilometers away. That's the challenge scientists face. To make it possible, telescopes use special instruments called coronagraphs. These block out the starlight, allowing the dim glow of the planet to appear. In some cases, interferometers combine the light from multiple telescopes to sharpen the image even further. The planets we've imaged directly are usually massive gas giants orbiting far from their stars. They glow faintly in infrared light,
because they're still hot from their formation. One famous example is the HR 8799 system, where astronomers have captured images of multiple giant planets orbiting together. Direct imaging isn't just about pretty pictures. It allows scientists to study a planet's atmosphere, temperature, and even cloud patterns. As technology improves, we may one day capture images of Earth-sized planets in habitable zones, maybe even seeing oceans, continents, or weather on their surfaces. The dream is to one day photograph a pale blue dot orbiting another star, a direct image of a potentially habitable world. That moment would change our perspective forever.
One of the strangest and most powerful techniques for finding exoplanets is called gravitational microlensing. It relies on a prediction from Einstein's theory of general relativity: gravity bends light. Here's how it works. When a star passes in front of a more distant background star, its gravity acts like a lens, bending and magnifying the light of the background star. For a short time, the star looks brighter to observers on Earth. If the closer star has a planet, the planet's gravity adds a smaller extra blip to the light curve. These little distortions reveal the presence of planets we could never see otherwise. Microlensing can detect planets that are far from their stars, or even rogue planets drifting freely in space. It's one of the few methods that can find Earth-sized worlds at great distances from us. The catch is that microlensing events are rare and unpredictable. The alignment of stars has to be just right, and the event may only last for days or weeks. Once it's over, we may never see that exact event again. Despite this, microlensing has uncovered planets across the galaxy, showing us that planetary systems form in all kinds of environments. Future missions, like the Nancy Grace Roman Space Telescope, will make this method even more powerful, possibly detecting thousands of new worlds. Microlensing is a reminder that sometimes the universe itself provides the tools for discovery. All we need to do is watch carefully when the light bends.
The discoveries we've made so far are only the beginning. The next generation of space telescopes will take us deeper into the world of exoplanets than ever before. Right now, the James Webb Space Telescope is already transforming the field. Its infrared vision lets us study the atmospheres of distant planets, detecting molecules like carbon dioxide, methane, and water vapor. It's the first step towards searching for real signs of life. But Webb won't be alone. The Nancy Grace Roman Space Telescope, planned for launch in the coming years, will use both microlensing and direct imaging to find thousands of new worlds, including those similar to Earth. Further ahead, projects like LUVR and HabX, still in the concept stage, could be true game changers. These proposed telescopes would be large enough and sensitive enough to take direct pictures of Earth-like planets around nearby stars, showing us their colors, their atmospheres, and maybe even their oceans and clouds. Some designs include giant star shades, huge flower-shaped spacecraft flying in formation with a telescope, blocking the starlight so planets can shine through. With tools like that, we could study alien worlds with incredible detail. Each new telescope brings us closer to answering one of humanity's biggest questions: are we alone? The next few decades may give us the first real clues. Finding planets is only the first step. The ultimate goal is to discover life beyond Earth. But how can we detect something so far away? Scientists look for what are called biosignatures, clues in a planet's atmosphere or surface that suggest life might be present. On Earth, oxygen is a big one. Our atmosphere is filled with it because plants and microbes constantly produce it. Without life, oxygen would quickly disappear. Methane is another clue, especially if it's found alongside oxygen. The two gases don't last together for long unless something keeps replenishing them. Detecting both could be a strong hint of biology at work. Water vapor is critical too. While it doesn't prove life, it shows that a planet has the right conditions for it. Clouds, seasonal changes, or even strange color patterns on a planet's surface could also reveal activity we can't explain with geology alone. The challenge is that none of these signs are proof by themselves. Volcanoes, chemical reactions, or other processes can mimic biosignatures. That's why scientists focus on combinations of signals that are harder to explain without life. With new telescopes, we're starting to scan exoplanet atmospheres for these fingerprints. The day we find a clear biosignature, a mix of gases or features that point strongly to biology, would be one of the most important discoveries in human history. It would mean that life isn't unique to Earth. It would mean the universe is alive. The idea of humans living on a planet around another star sounds like science fiction, but it's also a question scientists take seriously. For a planet to be suitable for us, it would need more than just the right temperature. It would need a breathable atmosphere, liquid water, and protection from deadly radiation. Gravity should be close to Earth's so our bodies could adapt. Too strong and moving would feel impossible. Too weak and our muscles and bones would weaken over time. There are also challenges with distance. Even the closest exoplanet, Proxima Centauri b, is more than 4 light-years away. With today's spacecraft, it would take tens of thousands of years to get there. For now, traveling to exoplanets is far beyond our reach. Still, it's fun to imagine. A super-Earth with lush forests and endless oceans. A water world with floating cities. Or even a moon around a gas giant where the sky is filled with swirling bands of color. If we ever find a truly Earth-like exoplanet, it could become a long-term goal for humanity. A new world where future generations might one day set foot. For now, exoplanets remind us of possibility. They show us that Earth is not the only type of planet the universe makes, and maybe not the only home for life.
When we think of skies, we imagine Earth's familiar blue. But on exoplanets, the skies could look wildly different. An atmosphere is more than just air. It's the planet's shield, climate system, and sometimes the key to life. Using powerful telescopes, astronomers can study starlight as it filters through an exoplanet's atmosphere. Different gases absorb different colors of light, leaving behind patterns that reveal what the air is made of. On a scorching hot Jupiter, the atmosphere might be thick with hydrogen and helium, with clouds of vaporized metals like titanium or iron. The skies there wouldn't be blue, they could glow orange, red, or even green. Some of these planets may even rain molten glass sideways in violent winds. On cooler super-Earths, the air could be heavy with carbon dioxide, nitrogen, or water vapor. If the planet has plants or alien microbes, its atmosphere could carry the fingerprints of life, oxygen, methane, or other unusual gases. Imagine standing on a distant world and looking up. You might see twin suns setting at once, a hazy purple sky thick with methane, or swirling auroras powered by a magnetic field far stronger than Earth's. Studying these alien skies isn't just about curiosity, it's one of our best tools for detecting whether a planet is habitable, and maybe even inhabited. In 2017, astronomers made a discovery that electrified the world. 7 Earth-sized planets orbiting a single star, just 40 light-years away. This star is called TRAPPIST-1,
a small, cool red dwarf. What makes TRAPPIST-1 so special is that 3 of its planets sit in the habitable zone, the region where liquid water could exist. That's 3 potential Earths, all in one system. The planets are packed tightly together, orbiting closer than Mercury does to our Sun. That means if you stood on the surface of one, you might actually see the neighboring planets looming large in the sky, like giant moons. Their orbits are so compact that a year there lasts only a few days or weeks. Scientists have already begun studying their atmospheres using powerful telescopes. We don't yet know if they have oceans, clouds, or even air at all, but the possibilities are staggering. TRAPPIST-1 could hold answers to some of humanity's biggest questions. Are we alone? Does life thrive around other stars? For now, we know this. TRAPPIST-1 isn't just another star system. It's a whole miniature laboratory of worlds waiting for us to explore.
The nearest star to our Sun is Proxima Centauri, a small red dwarf just over 4 light-years away. Orbiting it is an exoplanet called Proxima Centauri b, the closest potentially habitable world we've ever found. Proxima b is roughly the size of Earth and sits in its star's habitable zone. If it has an atmosphere, it could support liquid water on its surface. That's why it excites scientists so much. It's right next door, at least on a cosmic scale. But living there wouldn't be easy. Red dwarfs like Proxima Centauri flare often, blasting the planet with intense radiation. Without a strong magnetic field or thick atmosphere, life would struggle to survive. The skies might glow with constant auroras, but they'd be dangerous ones. Still, Proxima b is our best chance at a nearby Earth-like planet. Missions like Breakthrough Starshot have even suggested sending tiny laser-powered spacecraft to visit it. The journey would still take decades, but it would be humanity's first step toward the stars. Proxima Centauri b is a reminder that another Earth could be waiting just beyond our solar system. And one day, we might find out for sure.
Among the most common types of exoplanets we've discovered are worlds known as super-Earths. These are planets larger than Earth, but smaller than Neptune, typically 2 to 10 times our planet's mass. What makes them fascinating is that we don't have one in our own solar system. That means every time we study a super-Earth, we're looking at something completely alien to our experience. Some super-Earths may be rocky, with mountains taller than Everest and gravity so strong that walking would feel like carrying double your weight. Oceans there could be hundreds of kilometers deep, crushing everything beneath them into strange forms of ice that don't even exist on Earth. Others might have thick atmospheres, trapping heat and creating supercharged greenhouse effects. Imagine skies permanently red or orange, with storms that last for centuries. And then there are the so-called water worlds, super-Earths completely covered by vast, endless oceans. These could be some of the best places to look for alien life, hidden beneath their waves. For astronomers, super-Earths are exciting because they're easier to detect than smaller Earth-sized planets, and there are so many of them. If life is common in the universe, there's a good chance that at least some of it lives on a super-Earth. The big question is whether such worlds would be hospitable to us, or whether their crushing gravity and alien chemistry would make them impossible to call home. Either way, super-Earths remind us that Earth is not the blueprint for all planets. The universe builds many kinds of worlds, some stranger and larger than we can easily imagine.
Not all planets live in the warm embrace of a star. Some wander the galaxy alone, drifting through the dark. These are called rogue planets. Astronomers believe there could be more rogue planets than stars in our galaxy.
They form in star systems like normal planets, but are later flung out by gravitational interactions. Once exiled, they roam endlessly, invisible against the blackness of space. At first, rogue planets might seem like dead, frozen rocks. Without sunlight, their surfaces could be unimaginably cold. But some might still hold heat deep inside, from their formation or from radioactive decay in their cores. That hidden warmth could sustain underground oceans, sealed beneath thick layers of ice. If that's true, rogue planets could be secret havens for life. Warm, isolated biospheres traveling through interstellar space. Life there would never see a sunrise. It would live in eternal night, perhaps powered by geothermal vents, much like the strange creatures in Earth's deep oceans. For humans, rogue planets would be a nightmare to colonize. No sunlight for crops, no warmth for survival. Yet in theory, advanced civilizations might build domed cities powered by nuclear energy, turning these moving worlds into moving fortresses between the stars. The existence of rogue planets reminds us that the universe doesn't just make Earth-like worlds. It creates strange possibilities, planets that thrive even in the loneliest parts of space.
Between Earth-sized planets and gas giants like Neptune lies a strange and common class of worlds, Mini-Neptunes. These planets are larger than Earth, but smaller than Neptune, and they're some of the most puzzling objects in the galaxy. We're not sure if Mini-Neptunes are scaled-down gas giants with thick atmospheres of hydrogen and helium, or if they're rocky worlds with deep oceans and dense clouds. Some might even be covered in layers of exotic ice under crushing pressure. What makes them so fascinating is that they don't exist in our solar system. We have rocky planets like Earth and gas giants like Jupiter, but nothing in between. Mini-Neptunes seem to be everywhere else, yet missing here. Why? No one knows for sure. If they have thick atmospheres, these worlds might be too hostile for life as we know it. Temperatures could soar under greenhouse effects, and the pressure might crush anything on the surface. But if some Mini-Neptunes shed their atmospheres over time, they could evolve into smaller, more Earth-like planets. Studying these planets may reveal why our solar system looks the way it does, and whether Earth is more unusual than we think. Mini-Neptunes remind us that the universe doesn't always follow the same rules we see at home. Out there, planetary variety is far greater than we ever imagined.
Some of the first exoplanets ever discovered were hot Jupiters. Gas giants like Jupiter, but orbiting extremely close to their stars. Unlike our Jupiter, which takes 12 years to orbit the Sun, hot Jupiters can circle their stars in just a few days. Their closeness makes them scorchingly hot, often thousands of degrees. Their atmospheres boil under the relentless radiation, with winds blowing faster than the speed of sound. In some, molecules like water or methane are ripped apart by the intense heat. These planets are so near their stars that many are tidally locked, one side in permanent day, the other in eternal night. The day side may glow like a furnace, while the night side freezes in shadow. Between them lies a twilight zone of extremes. Astronomers still debate how hot Jupiters form. They probably didn't form so close to their stars where conditions are too violent. Instead, they may have formed farther out and then migrated inward, pulled by gravity until they reached their current orbits. Though they're unlikely to host life, hot Jupiters are invaluable to science. Their large size and dramatic atmospheres make them easier to study. By observing them, astronomers learned how to detect exoplanets in the first place. In a way, hot Jupiters were our introduction to the diversity of worlds beyond our solar system,
showing us that nature makes planets stranger than anything we expected.
Not every planet in the habitable zone is actually habitable. Being at the right distance from a star is just the beginning. Many other factors determine whether life could exist. Atmosphere is crucial. Too thin, and the planet freezes. Too thick, and it traps heat like Venus, creating a runaway greenhouse effect. Magnetic fields help shield the surface from dangerous radiation, protecting any potential life. Without one, even a planet in the perfect spot could be baked or irradiated. The planet's composition matters too. Rocky surfaces with liquid water are ideal, but gas giants or icy worlds might lack a solid surface for life to develop. Even the planet's rotation could influence climate. Tidally locked planets where one side faces the star constantly might have extreme temperature differences between day and night sides. Then there is stellar behavior. Some stars flare violently, sending bursts of X-rays and ultraviolet radiation that can strip atmospheres and sterilize the surface. Others are stable, providing a calm, long-lasting environment where life could evolve. Habitability is a delicate balance. Earth exists in just the right spot. With the right atmosphere, magnetic field, and stable star, tiny changes in any of these factors could make our planet unlivable. When we look at exoplanets, scientists search for that balance, a combination of distance, atmosphere, composition, and protection that makes life possible. Even planets that seem perfect at first glance may hide deadly surprises, reminding us that life is fragile and special.
Some exoplanets may be covered entirely by water, earning them the nickname water worlds. Unlike Earth, which has continents and oceans, these planets might have no land at all, just endless, deep oceans stretching as far as the eye can see. Water worlds are exciting because water is essential for life as we know it. If conditions are right, these planets could host alien oceans, teeming with microbial life, or even larger creatures adapted to extreme pressures and temperatures. The depth of these oceans could be extreme. On some super-Earth water worlds, water may extend hundreds of kilometers deep, creating layers of high-pressure ice at the bottom. Life, if it exists, would have to survive under these crushing conditions, perhaps around hydrothermal vents, similar to those on Earth's ocean floor. But water worlds also pose challenges. Without land, there's no erosion, no cycles to recycle nutrients from rocks, and weather patterns would be very different. The balance between oceans, atmosphere, and temperature would determine if life could thrive. Water worlds remind us that life could exist in forms and environments far beyond our imagination. They expand our view of what a habitable planet might look like, showing that alien oceans could be just as important as alien skies.
Some exoplanets are tidally locked, meaning one side always faces their star while the other side remains in permanent darkness. This happens when a planet's rotation matches its orbit, creating extreme conditions. The day side can be scorching hot, blasted by constant starlight, while the night side freezes in total darkness. Temperatures could vary by hundreds of degrees between the two hemispheres. Winds may rush from the hot side to the cold, creating massive, never-ending storms along the twilight line, where day meets night. Tidally locked planets are common around red dwarf stars, which are smaller and cooler than the Sun. Their habitable zones are close in, increasing the chances of tidal locking. Life on such a planet, if it exists, would have to adapt to extremes. Perhaps it survives in the narrow twilight zone, where temperatures are milder. Maybe organisms hibernate on the dark side and thrive on the warm side. These worlds challenge our ideas of habitability. Life might not need Earth-like day-night cycles or moderate climates. Even planets with one side perpetually burning and one side frozen could still host life in ways we've never experienced.
Some exoplanets experience weather so extreme it's hard to imagine. Gas giants close to their stars, like hot Jupiters, have winds that can reach thousands of kilometers per hour, circling the planet in a single day. On some worlds, storms last for centuries without stopping. On HD 189733b, winds blow molten glass sideways across the skies. On WASP 76b, iron vapor condenses on the cooler night side, falling as liquid metal rain. These are storms far beyond anything on Earth, where weather can destroy entire landscapes in minutes or hours. Even rocky planets can experience extreme weather. Tidally locked planets have perpetual day and night sides, creating violent storms along the boundary between the two. Water worlds could have planet-wide hurricanes fueled by endless oceans. Studying these alien weather patterns teaches us how atmospheres behave under conditions we can't replicate on Earth. It also gives clues about what life could survive and how planets evolve over time. Extreme weather reminds us that the universe is full of worlds that are both beautiful and dangerous, far beyond the calm skies we take for granted on our own planet.
Not all planets have seasons like Earth. On some exoplanets, a year might last only a few days. On others, it could stretch for centuries. Tilt, orbit shape, and rotation all influence the planet's climate cycles. Tidally locked planets have no traditional seasons. One side is always in sunlight, the other in darkness. But planets with eccentric orbits, where the distance from their star changes drastically, can experience extreme temperature swings. A summer at closest approach might scorch the surface, while a winter far from the star freezes oceans solid. Super-Earths and water worlds could have unusual seasonal patterns. Vast oceans might create planet-wide monsoons, while tilted planets might experience intense shifts in climate, more severe than anything on Earth. On some gas giants, seasons may be marked by massive storms, swirling endlessly over colored bands in the atmosphere. Understanding exoplanet seasons helps us imagine life there. Organisms would need to adapt to extreme cycles, from constant daylight to violent climate swings. The variety shows that even something as familiar as a year can be completely alien on other worlds.
Not all planets are made like Earth. Some exoplanets are composed of materials we rarely see in our solar system, creating truly exotic worlds. Take carbon planets, for example. These could be rich in graphite or even diamonds. A planet like 55 Cancri E might have a crust made of graphite and diamond, with molten lava flowing beneath. Imagine a world sparkling with crystals instead of water or rock. Other planets might be ocean worlds, entirely covered by water, with no continents at all. Some gas giants contain exotic clouds made of ammonia, methane, or even silicate particles. Their skies could be red, green, or violet, depending on chemical reactions in the atmosphere. Even planets with unusual cores exist. Some super-Earths might have iron-rich interiors, creating enormous magnetic fields, while others could be icy worlds, with frozen layers hundreds of kilometers thick. Studying these compositions teaches us how diverse planetary formation can be. The universe doesn't just make Earth-like planets, it builds worlds of unimaginable variety,
where the rules of geology and climate are stretched to extremes. Not all planets stay where they formed. Many migrate, moving closer to or farther from their stars over millions of years. This process, called planetary migration, reshapes entire solar systems. Hot Jupiters are a prime example. They likely formed far from their stars, where it was cool enough for gas to accumulate. Then, over time, gravitational interactions with other planets or the protoplanetary disk pushed them inward, creating the scorching giants we observe today. Migration isn't limited to gas giants. Super-Earths and Mini-Neptunes may also drift, changing their temperature, atmosphere, and potential habitability. A planet that starts in a frozen region could move into the habitable zone, warming up and potentially developing oceans. Migration can be chaotic. Planets can collide, eject one another from the system, or form resonances where their orbits are perfectly timed. These movements create dynamic, often surprising planetary architectures. Understanding planetary migration helps us explain why exoplanet systems are so different from our own. It shows that planets aren't fixed, they're part of a cosmic dance, moving and evolving over billions of years.
Many stars in the galaxy aren't alone. They have a companion. Binary star systems, where two stars orbit each other, create complex environments for planets. Some exoplanets orbit one star in the pair, while others orbit both, creating a true circumbinary world. Planets orbiting two suns are rare but fascinating. Imagine standing on the surface and seeing two suns rise and set, casting double shadows across the landscape. The climate could be wildly unpredictable, with heating varying depending on the stars' positions. Binary stars can make life tricky. Gravitational forces from both stars can destabilize orbits, ejecting planets or causing extreme seasons. Yet some planets manage to survive in stable orbits, offering unique conditions for alien life. Kepler 10b is a famous example, a gas giant orbiting two stars. While not habitable, it proves that planets can exist in these complex systems. If rocky, Earth-like planets exist in similar setups, their skies could be filled with fascinating patterns of light and shadow. Binary star systems show that the universe doesn't limit itself to simple setups. Planets can thrive even in dynamic multi-star environments, adding another layer of wonder to the search for life.
Just like Saturn in our solar system, exoplanets can have rings and moons. These features add complexity to the planet's environment and can influence habitability. Exomoons are particularly exciting because they could host life themselves. A large moon orbiting a gas giant in the habitable zone might have oceans, atmospheres, and even stable climates. Moons can also experience tidal heating, stretching and squeezing by their planet's gravity, which provides extra warmth for life, similar to Jupiter's moon Europa. Rings, on the other hand, are not just decorative. They can impact the planet's climate and even protect moons from meteoroid impacts. Detecting rings around exoplanets is difficult, but scientists can infer them from subtle changes in starlight as the planet passes in front of its star. Some planets may have systems of multiple moons, forming miniature solar systems of their own. Imagine a planet with a sky filled with several moons, each casting shadows and affecting tides on the surface. Studying rings and moons shows us that planets aren't isolated objects. They exist in systems with companions that shape their evolution, climate, and possibly the chances for life.
One of the most successful ways to find exoplanets is the transit method. It's simple in concept, but powerful in practice. When a planet passes in front of its star from our point of view, it slightly dims the star's light. By measuring these tiny dips repeatedly, astronomers can determine the planet's size, orbit,
and even some atmospheric properties. This method has led to the discovery of thousands of exoplanets, especially smaller Earth-sized worlds that are otherwise difficult to detect. Kepler and TESS have relied on transits to scan millions of stars, revealing the diversity of planets in our galaxy. Transit observations can also hint at moons, rings, or atmospheric composition. By analyzing the starlight that filters through the planet's atmosphere during a transit, scientists can detect water vapor, carbon dioxide, and other gases. The transit method shows that small changes in light can reveal entire worlds. It's a testament to human ingenuity. We don't need to see a planet directly to study it.
Another powerful technique for finding exoplanets is the radial velocity method, sometimes called the Doppler method. Instead of looking for a planet itself, astronomers watch the star, listening for tiny wobbles caused by the gravitational pull of orbiting planets. Every planet tugs on its star as it orbits. For large planets like gas giants, this wobble is easier to detect. For smaller Earth-like planets, the motion is minuscule, often smaller than a walking pace, but advanced instruments can measure it. By studying these shifts in starlight, astronomers can determine the planet's mass, orbit, and sometimes even hints of additional planets in the system. Combining radial velocity with the transit method gives even more information. For instance, it allows scientists to calculate a planet's density, telling us whether it's rocky like Earth or gaseous like Neptune. It also helps verify discoveries made by other methods, ensuring the planet is real and not just a signal from the star itself. This method has uncovered some of the earliest exoplanets, including 51 Pegasi b, the first confirmed planet orbiting a Sun-like star. It has opened our eyes to worlds we can't see directly, proving that the tug of a planet on its star is enough to reveal its existence. The radial velocity method reminds us that even invisible planets can leave unmistakable fingerprints. By listening carefully to the stars, we've mapped thousands of worlds across the galaxy.
The habitable zone is the region around a star where a planet could have liquid water on its surface, often called the Goldilocks zone because conditions aren't too hot and aren't too cold. Being in the habitable zone doesn't guarantee life, but it's an important first filter. Too close to the star and water boils away, leaving a dry, lifeless world like Venus. Too far and water freezes, like on Mars or Europa. Just right, and a planet could maintain oceans, rivers, and potentially life. The size and type of the star change the habitable zone. Around smaller red dwarfs, the zone is very close, increasing the chances of tidal locking. Around larger stars, the habitable zone is farther out, but the star's intense radiation may challenge life. Scientists are especially interested in planets that not only lie in the habitable zone, but also have stable atmospheres and protective magnetic fields. These factors increase the odds that liquid water, and maybe life, could persist for billions of years. The habitable zone helps narrow our search for life in a galaxy filled with planets. It's a reminder that even in an infinite universe, only some worlds have the right conditions to support life as we know it.
Proxima Centauri b is the closest known exoplanet to our solar system, orbiting the red dwarf Proxima Centauri, just over 4 light-years away. Its proximity makes it an object of intense interest for scientists and space enthusiasts alike. This planet is roughly Earth-sized and sits in the star's habitable zone. If it has an atmosphere, it could host liquid water, making it a prime candidate in the search for life. However, living there wouldn't be easy. Red dwarfs like Proxima Centauri are prone to violent flares, which could strip the planet's atmosphere or irradiate its surface. Proxima b might be tidally locked, with one side in constant daylight and the other in eternal night. Life, if it exists, might survive in the narrow twilight zone between scorching and freezing extremes. Scientists speculate that microbial life or even simple ecosystems could persist underground or in protected regions. Proxima b also sparks imagination about interstellar travel. Projects like Breakthrough Starshot propose sending tiny spacecraft to the planet, which could arrive within decades. While this is still theoretical, it's the first step toward exploring a planet outside our solar system up close. Proxima Centauri b represents hope and curiosity. It's a reminder that the nearest exoplanets are not just distant points of light. They are worlds with potential for discovery, maybe even life, waiting just a few light years away.
The James Webb Space Telescope, or JWST, is transforming our understanding of exoplanets. Unlike earlier telescopes, Webb can see in infrared, allowing it to study the heat and chemical composition of distant worlds. By observing a planet as it passes in front of its star, Webb can analyze the starlight that filters through the planet's atmosphere. This reveals gases like water vapor, carbon dioxide, methane, and even exotic chemicals. Detecting these molecules is crucial for identifying potentially habitable planets and searching for signs of life. JWST can also measure the temperature of exoplanets, map clouds, and even detect winds in their atmospheres. On hot Jupiters, it can track day-night temperature differences, giving scientists insight into extreme weather patterns. Future discoveries with Webb could include Earth-like planets with detectable atmospheres, perhaps even hinting at life. This telescope isn't just a tool. It's a window into alien worlds, letting us study planets that were once invisible points of light. With Webb in space, the era of exoplanet science has entered a new chapter. We can now move from finding planets to understanding them in detail, from cataloging worlds to exploring the conditions that might support life.
Finding an exoplanet is just the first step. The ultimate goal is detecting life. Scientists search for biosignatures, indicators that life may exist on a distant world. A key biosignature is atmospheric oxygen. On Earth, oxygen is produced by plants and microorganisms, and without life, it would disappear over time. Methane is another important clue, especially if found alongside oxygen, because the two gases react with each other and would not coexist without a continuous source. Water vapor, clouds, and seasonal atmospheric changes can also hint at a habitable environment. Even unusual colors or reflective patterns on a planet's surface might indicate biological activity. Detecting biosignatures is incredibly challenging. Non-biological processes like volcanoes or chemical reactions can mimic these signals, so scientists look for multiple lines of evidence. By combining observations of gases, temperature, and surface features, they can build a stronger case for the presence of life. With telescopes like JWST and future missions, we are entering an era where the first true signs of life beyond Earth could be detected. Every atmospheric fingerprint brings us closer to answering humanity's most profound question: are we alone in the universe?
As we discover exoplanets, humans naturally wonder, could we live on them? This leads to the idea of terraforming, modifying a planet's environment to make it habitable. Terraforming is a colossal challenge. Planets would need a stable atmosphere, liquid water, manageable temperatures, and protection from radiation. For example, a planet orbiting a red dwarf might need artificial magnetic shields or atmosphere-thickening technologies to survive stellar flares. Gravity is another factor. Super-Earths may be too strong for humans to move comfortably, while smaller planets could weaken muscles and bones over time. Even if full terraforming is centuries away, studying exoplanets helps us imagine possibilities. Domed cities, underground habitats, or floating colonies on water worlds are potential ways to adapt. Life might exist in zones where temperatures and light are more moderate, or engineered ecosystems could sustain human life in extreme conditions. Terraforming remains science fiction for now, but as we explore alien worlds, it inspires innovation and imagination. Each exoplanet discovery fuels dreams of expanding humanity beyond Earth, reminding us that the universe holds limitless possibilities.
Among the thousands of exoplanets discovered, some are exceptionally rare and strange, defying expectations. These outliers teach us about the universe's creativity and diversity. Some planets orbit multiple stars, creating complex gravitational dances. Others, like ultra-short period planets, circle their stars in less than a day, enduring intense heat and radiation. Rogue planets drift alone through the galaxy, unseen by their stars, while carbon-rich planets could have crusts made of graphite or diamonds. Even water worlds, super-Earths, and mini-Neptunes are considered unusual from a solar system perspective. Their compositions, atmospheres, and orbits reveal that planetary systems elsewhere can be far stranger than our own. Studying rare exoplanets helps scientists refine theories of planet formation and evolution. Each discovery challenges assumptions about what's normal in the cosmos, showing that the universe doesn't follow a single blueprint. Rare planets remind us that the galaxy is full of surprises. They hint at alien worlds unlike anything on Earth and expand our imagination about what planets and life might be like.
When we think of planets, we imagine Earth's blue oceans or Mars's red deserts, but exoplanets may look completely different, with skies and surfaces and colors we can barely imagine. Hot Jupiters might glow orange or red, their thick atmospheres filled with vaporized metals. Water worlds could appear deep blue, reflecting sunlight off endless oceans. Gas giants may have swirling bands of green, purple, or violet, shaped by exotic chemical reactions in their clouds. Even smaller rocky planets might surprise us. Planets rich in carbon could sparkle with graphite or diamond surfaces. Some may have skies tinted by thick hazes of ammonia or methane, creating sunsets unlike any on Earth. By studying the colors of exoplanets, astronomers gain insight into their atmospheres, compositions, and even weather patterns. Spectroscopy allows us to decode these alien colors, turning faint light into detailed information about worlds we cannot visit.
The future of exoplanet discovery is bright. Upcoming missions and advanced telescopes promise to reveal planets we cannot even imagine today. The European Extremely Large Telescope, under construction in Chile, will be the largest optical telescope ever built. Its enormous mirror will allow direct imaging of Earth-like planets around nearby stars. Observatories like these will let scientists study exoplanet atmospheres in unprecedented detail, searching for signs of water, clouds, and even life. Space missions like the Nancy Grace Roman Space Telescope and proposed projects such as LUVOIR and HabEx aim to find thousands of new worlds. Some designs include giant star shades that block starlight,
allowing telescopes to see faint planets directly. Others will scan millions of stars for subtle wobbles or transits, expanding our catalog of exoplanets dramatically. These missions could answer fundamental questions. How common are Earth-like planets? What conditions make life possible? Could we one day identify worlds where life actually exists? The next decades may finally turn exoplanet exploration from distant observation into detailed study, pushing humanity closer to understanding our place in the cosmos. Every new mission brings us one step closer to seeing the universe as it truly is, alive with possibilities.
Even with thousands of exoplanets discovered, reaching them is another challenge entirely. The nearest stars are light years away, and with current technology, it would take tens of thousands of years to get there using conventional spacecraft. Projects like Breakthrough Starshot propose tiny, laser-propelled probes capable of traveling up to 20% the speed of light. These miniature spacecraft could reach nearby systems like Proxima Centauri in a few decades, sending back images and data about planets previously only studied from afar. The challenges are immense. Protecting these probes from interstellar dust, maintaining instruments over decades of travel, and transmitting data across light years all require revolutionary engineering. For humans, the obstacles are even greater. Life support, radiation shielding, and the effects of long-term space travel on the body are daunting. Yet the dream of interstellar travel drives innovation. Even planning missions to nearby exoplanets expands our understanding of propulsion, materials, and long-term sustainability. It transforms the search for exoplanets from observation into a roadmap for exploration.
Beyond finding planets and signs of life, scientists are searching for intelligent civilizations. The search for extraterrestrial intelligence, SETI, focuses on detecting signals that cannot be explained by natural processes. Exoplanets in the habitable zone are prime targets. A planet with liquid water, a stable atmosphere, and a long-lasting star might not only host life, it could harbor civilizations capable of communication. Radio signals, laser pulses, or unusual energy patterns could all hint at intelligence. Some scientists also consider megastructures like Dyson spheres, which could be detectable through irregular dips in starlight. Observing these anomalies might reveal that a civilization has advanced technology beyond our imagination. While no definitive signs of intelligence have been found yet, the discovery of thousands of exoplanets increases the odds. Every new planet is another possibility, a potential home for life that has developed its own culture, science, and technology. The search for intelligence transforms exoplanets from mere scientific curiosities into potential mirrors of our own civilization, challenging us to think about life on a cosmic scale.
The universe is vast, and with it comes an almost unimaginable diversity of planets. From scorching hot Jupiters to frozen rogue worlds, from water worlds to diamond-covered planets, the variety is staggering. Each discovery expands our understanding of what's possible. Exoplanets challenge our assumptions about planetary formation, habitability, and the uniqueness of Earth. Some are strange beyond imagination, planets with twin suns, extreme eccentric orbits, or thick alien clouds that paint the skies in colors we've never seen. Studying these worlds teaches us that the cosmos doesn't follow a single blueprint. Nature experiments, creating endless variations on the theme of planets. Every new system is a miniature universe in itself, with its own rules, climates,
and possibilities for life. This perspective changes how we view our place in the universe. Earth is precious, but it is just one of countless worlds. The multiverse of planets reminds us that the galaxy is full of mysteries, waiting for curious minds to explore, imagine, and understand.